In this module, we are discussing the basics of particle acceleration and detection methods. In this video, you will see how different technologies are combined to build the two basic types of particle detectors, namely spectrometers and calorimeters. At the end of this video, you will be able to describe how a spectrometer measures the direction and momentum of a charged particle in a non-destructive manner, and to describe how a calorimeter measures the direction of energy of a particle by total absorption. You will also be able to identify the strength of these two basic methods and their synergy. A magnetic spectrometer is used to measure the direction and momentum of a particle with minimal interaction. It is a non-destructive method to measure these properties. The particle trajectory is measured in a known magnetic field. For a homogeneous field, the trajectory is a spiral, a circle in the plane orthogonal to the field, and a straight line in the direction of the field. The radius of curvature is proportional to what is called the magnetic rigidity R, which is the ratio between the momentum P and the charge Z. R is equal to P over Z and can be measured by the product of the radius of curvature and the magnetic field. The magnetic field itself is provided by a permanent magnet or an electromagnet. Measurements of the path are performed by an ionization detector, a gas-filled wire chamber, for example, or layers of semiconductor detectors. The tangent to the trajectory at the entry of the magnet gives the direction of the incident particle. As an example, here's again a photo of the drift chamber from the L3 experiment at the Large Electron-Positron Collider at CERN, as well as a picture of an E+, E- annihilation into hadrons on the right side. The reaction takes place in the middle of the device, the center of the image on the right. In the central part, you see the tracks of charged particles in yellow reconstructed from the measured coordinates indicated by the small green crosses. The curvature is barely visible, but well measured by the high-resolution drift chamber. In this photograph on the left, you see the central detector, a central detector made out of silicon sensors, the one that is used by the ATLAS experiment. The right image is the reconstruction of a reaction between protons in the middle of the device. The charged particles which are produced leave tracks forming circles orthogonal to the magnetic field. The purpose of a calorimeter is to measure the energy and direction of particles by absorbing them. The principle of operation is the following. The incident particle initiates a shower of particles in the detector, an electromagnetic shower or a hadronic shower. The shape, size and composition of the shower depends on the incident particle, but also on the detector materials, namely its radiation length, its nuclear interaction length. The energy is deposited in the form of heat, which is not very useful, but also produces detectable signals like ionization and excitation by DEDX, scintillation light, Cherenkov radiation, etc. This energy is detected by sensors. The resulting signal is proportional to the total energy deposited by the particle of the shower in the active medium of the detector. There are two kinds of calorimeters: homogeneous ones, with only one material to absorb and detect the shower particles, and layered calorimeters, which use different materials for interaction or absorption and detection. Here's an example of a layered calorimeter. In such a calorimeter, layers alternate. There are absorption layers made of heavy materials like copper, lead or uranium with a short radiation and hadron interaction length. Here particles interact and form the shower. In the sensitive layers, the energy loss by DEDX is recorded. These layers may be equipped with a gaseous or noble liquid proportional chamber, a semiconductor sensor or a scintillator. You see here the electromagnetic calorimeter of ATLAS, which contains absorption layers of lead and steel alternating with sensitive layers filled with liquid argon. The whole has a shape resembling an accordion. In a homogeneous calorimeter, on the other hand, the two functions are combined. The same material is used as an absorber and as a detector for deposited energy. Scintillators made of heavy materials can be used like bismuth germanate, BGO, or lead tungstate. Because of the short radiation length and the transparency of these materials, they are often used to detect electromagnetic showers. The scintillation light emitted by the electrons of the shower is detected either by photomultipliers or by semiconductor photodiodes, as in this example, which shows you the lead tungstate calorimeter of the CMS experiment at the LHC. Calorimeters are also one of the main applications of plastic scintillator. The large calorimeter for hydrate showers of the ATLAS experiment is an example. Here you see a small animation showing the structure of one of its wedge-shaped slices. It uses scintillator tiles inserted between steel absorbers to measure the energy of hadrons. The shower develops mainly in the metal layers. The charged particles it generates produce scintillation light in the sensitive layers. The scintillation light is collected by optical fibers and guided to photo detectors. In this way, a three-dimensional image of the shower is measured, which allows to reconstruct direction and energy of hadrons. But also the Cherenkov effect allows to build complete detectors. The Super Kamiokande detector in Japan consists of a huge cylindrical tank which contains 50,000 tons of ultra-pure water. When a charged particle passes through the water at a speed beyond that of the speed of light in water, which is about 75% of the speed of light in vacuum, a cone of Cherenkov light is emitted. This cone is intercepted by an array of photomultipliers distributed on the walls. They detect an ellipse of photons, which allows to reconstruct the direction and velocity of the particle. Lateral and longitudinal segmentation allows to distinguish between hadrons and particles which interact only via the electromagnetic force, like electrons and photons or muons. As a general rule, one can say that electromagnetic showers are short, slim, and regular. Hadronic showers are penetrating, wide, and irregular. Because of the different characteristics of electromagnetic and hadronic showers, there are often two calorimeters, a fine-grained electromagnetic one and a coarser hadron calorimeter. But it is the synergy between different detector types that allows to both identify particles and measure their direction and energy. This is further explained in the optional video 3.10a, which shows how the ATLAS detector at LHC works. In the next video, we will show which types of particle detectors are developed and produced in our laboratories at the University of Geneva.